Hello everyone, we are students from the Faculty of Electrical and Electronic Engineering at University Tun Hussein on Malaysia. Today, we are excited to present our group project for the course BEJ 10403, Electric Circuit 2. I am Azam Hakim bin Abdullah with the matric number DE250106, and I am joined by my group members Muhammad and Zul. Today, we are presenting our group project. So, our project is titled Second Order Circuit RLC and Sinusoidal Steady State Analysis, which focuses on two main areas of electrical engineering. First, we explore the dynamic behavior of parallel RLC circuits, specifically designed for overdamped, critically damped, and underdamped responses. Second, we perform a sinusoidal steady-state analysis on a multi-mesh network. Our primary goal is to apply advanced circuit analysis techniques to solve complex problems, and then we validate our theoretical calculations through Proteus simulation software. In this video, we will walk you through our detailed mathematical findings and the resulting simulation plots. Let's dive in.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zulaika bin Usli, DE250120, and now I will be presenting question 1 for this project. So here we have a parallel RLC circuit with an I source of 4 ampere and R value is unknown and 0.5 F for capacitor, L is unknown, and IT. So we have to assume the initial current IL at 0 and the initial capacitor voltage EC of 0 are both equals to 0. So for the design, choose the undamped frequency omega in the range of 100 to 1000 radian per second. So for our group, we choose 350 radian per second. So first, since we choose our undamped frequency as 350 radian per second, we have to find for L using the equation omega equals to 1 over sert LC. So put in the value omega as 350 and C as 0.5 F. We get our inductance L equals to 16.33 microhenry. So with that, throughout the design, inductance 16.33 microhenry will be our constant. So for the first case is critically damped, where alpha is equal to omega. So since alpha is equals to omega, our alpha will be 350, and using the equation alpha equals to 1 over 2 RC, we can find R as 2.857 milliohm. And then we found our characteristic route using the equation negative alpha plus minus sert alpha squared minus omega squared. With that, we get S1 and S2 equals to negative alpha. And then we choose our characteristic root as exponential negative alpha t A1 t plus A2, where A1 and A2 is our constant. So then we redraw the circuit for t more than 0 and apply initial condition. So since in this circuit IC is equals to C dV0 over dt, which then we can find dV0 over dt is equals to 8 volt per second. And then we put our characteristic root equation V of t equals to E negative alpha t A1 t plus A2. So since A1 and A2 is our constant, we have to find its value. So first we apply initial condition to to set equation, and we find that a2 is equals to 0, and then we find the derivative for the characteristic root equation. So to find the derivative, simply use product rule, uv prime plus vu prime, where u prime is e negative alpha t and our v is a1t plus a2. So then we get, and then we apply dv0 over dt, which is equals to 8, into the equation, and then we get our next equation as 8 equals to a1 minus 350 a2. So we can calculate the previous equation, a2 equals to 0, and this equation 8 equals to a1 minus 350 a2, and then we get a1 equals to 8 and a2 equals to 0. So apply those constants into the characteristic root equation, and then we get our vt as 8t exponential e negative 350 v per second. And then we have to find for it. So to find it, we use Kirchhoff current law, KCL. So it is equals to I source minus I at resistor minus I at capacitor. So with that, I source is 4, I at R is equals to V over R, and I at C is equals to C dV over dt. So then our final it value is 4 minus 1400t plus 4 exponential e negative 350t ampere. And moving on to the overdamped case. So for overdamped case, alpha is bigger than omega. So since omega is 350 reps per second, our alpha will be 700. So using the equation alpha equals to 1 over t RC, we get that R equals to 1.429 milliohm. So then we find our characteristic root S. So from the equation we get that S1 equals to negative 93.782 and S2 equals to negative 1306.218, and our characteristic root equation will be V over V of t equals to A1 ES1t plus A2 ES2t. So A1 and A2 will be our constant. So next we redraw for t more than 0 and apply initial condition. The same as before, we get that dv of 0 equals to dt, dv of 0 over dt equals to 8 volt per second, and applying initial condition to the previous characteristic root equation, Vt A1 E S1t plus A2 E S2t, we get that 0 equals to A1 plus A2. So this will be our first equation, and then we find the derivative for the characteristic root equation. We get negative 93.782 A1 E minus negative 93.782t minus 1306.1882 E negative 1306.18t. So applying initial condition of dv0 over dt, which is equals to 8, we get that the equation will be 8 equals to negative 93.782 A1 minus 1306.1882. So this will be our second equation to then simultaneously calculate the first equation, 0 equals to A1 plus A2, and the second equation. So we get that our constant A1 equals to 6.598 milli and A2 equals to negative 6.598 milli. So now we can find for VT and IT. For VT, we get 6.598 milli E negative 93.782 T minus 6.598 milli E negative 1306.218 T, which then simplify into 6.598 milli exponential negative 93.782 T minus E negative 1306.18 T volt. So for IT, using KCL, we get 4 minus 4.31 E negative 93.728 T plus 0.31 E negative 1306.218 T ampere. So lastly, for underdamped cases. So for underdamped case, alpha has to be less than omega. So with omega as 350 rep per second, our alpha will be 175. So using the equation alpha equals to 1 over 2 RC, our R will be 5.714 milliohm. So then we find our characteristic root. Instead, since we are on underdamped, it will be S equals to negative alpha plus minus J omega D. So the equation for omega D will be set omega 0 squared minus alpha squared. So with that, our omega D will be 303.109, and applying to the characteristic root, S1 will be negative 175 plus J303.109, and S2 will be negative 175 minus J303.109. And then we get our characteristic root equation, which is V of t equals to E negative alpha t A1 cos omega d t plus A2 sin omega d t. So then we redraw for t more than 0 and apply initial condition. Our dv0 over dt will be 8 volt per second. So then our Vt, our previous characteristic root equation, Vt equals to E negative alpha t A1 cos omega d t plus A2 sin omega dt. Apply initial condition to the previous equation and put in all the value. We get 0 equals to A1 cos 0 plus A2 sin 0. Since we know that sin 0 is equals to 0 and cos 0 equals to 1, we get A1 equals to 0 as our first equation. And then finding the derivative for the characteristic root equation using the product rule, we get this value, which then we apply dv0 over dt, which is 8 into the equation. We get 8 equals to negative 175 A1 plus 303.109 A2, which is, this is our second equation. So we can simultaneously calculate the first and second equation to get A1 equals to 0 and A2 equals to 0.0264, which make our Vt equals to 0.0264 E my negative 175 T sin 303.119 T volt. And then we find for IT using KCL, which is our IT will be 4 minus E negative 175 T 4 cos 303.109 T plus 2.31 sin 303.109 T ampere. And that is all from me for manual calculation for question 1.
Assalamualaikum. Now we go to calculation for question 2. Can you see a circuit? We have a parallel circuit. We have a VC1 and VC2. For VC1, a value is 1 to 0 cos 100t plus 90 degree, and VS2 at 80 cos 100 dV, and we group put R1 is equal to 50 ohms and inductance 1 equal to 50,100 millimeter Henry. So we now will convert times domains to frequency domain. For example, VC1 120 cos 100 T plus 90 degree, convert to frequency domain 120 phase 90 degree, and hands on. So we will go to the mesh method. For the first method, for full mesh, I1 50 plus I1 minus I2 J30 minus 120 90 equals 0, and we have one equation. And the second mesh, J40 I2 minus J200 I2 minus I3 minus J30 I2 minus I1 equals 0, and we got a second equation. And the third mesh, J50 I3 plus 10 I3 plus 80 0 degree plus J200 I3 minus I2 and 0. We have to substitute I3 into equation 2. So we got J30 I minus J190 I2 plus J200 in bracket minus 80 in bracket equation 3 in 2. So minus 80 plus J200 I2 over 10 plus J250. So after that we got equation 4. Now we will compare the two equation 4 and equation 1. We will write in matrix form. First, 50 plus J30 minus J30 J10 1.6 minus J189.94 I1 I2 equal 1 to 0 90 63.95 2.29. And now after that we found we will calculate for delta will got first matrix form. After that, we get the delta value. Next, we found the delta 1 value. Just replace the value, the last one, into the first column in the matrix form. So we get delta 1 value. After that, delta 2 value. Delta 2 value, we just replace value, the last one, to the second column and get a delta 2 value. After that, we can calculate I1 and I2. For example, I1 delta 1 over delta 2, delta 1 over delta, and we got the value of I1 and I2. So after that, we can get I3. For example, just input the value I2 in the equation 3. So when we have I1 and I1, I2, I3, we can get a V0. V0 equal to V minus Z200 equal Z1 and Zi and Z minus J200 equal I2 minus I3. After that, we can get a V0 equal 446.8 minus 171.61 voltage.
Alright, now moving on to the circuit simulation on Proteus. That's what we're going to be using today. So first things first, this is for Q1. So we would have to find the over, critical, and under damp graph to find it. So for over, from our calculation, we got R equals to 1M. For critical, we got R equals to 2.857 milliohm. And then for under, we got 5 milliohm. So from this, we will continue on to see the graph result for voltage. So simulate graph. Okay, so for C2 is for overdamp, and then for C1 is for critically damp, and then for C3, which is on blue, is going to be underdamp. So yep, green for over, red for critical, blue for under. So it's going to be the same for the current graphs. So if I simulate it here, simulate graph, there we go. This is a lot more apparent. And so for the green, it's still the same. It is the overdamp. So as you can see, this is the green values, the green graph. And then for red, which is for critically damp, is this line right here. And then for underdamp, it has this overshoot from the bottom thing. So yeah, that is all for Q1. Now we will move on to Q2. For Q2, we have chosen the values of 50 ohm, and 500 millihenries here. So let me go and debug this and run simulation. Okay, sorry, this is for Q1, this is for Q2. Now as you can see, the values aren't exact values as the calculation that we got, but it is close and similar to the answers. We have on I1 is equals to 1.4 on average, and then the I2 is 0.28 or 27. And then we have the voltage on C on the capacitor value, which is at around 53 to 55 voltage. That is all from me. Thank you very much.